There's a spacecraft right now hurtling through the darkness between stars, more than 12 billion miles from the nearest human being, running on decaying plutonium the size of a grapefruit, transmitting data at a speed slower than a 1980s dial-up modem. And it is telling us something that every model, every simulation, every theory we built about the edge of our solar system got completely wrong. Not slightly wrong, fundamentally wrong. And the strangest part, its twin brother went first, made history first, got all the headlines first, but it was blind. Only Voyager 2 could see. Nobody asked the question that mattered most. When Voyager 1 crossed into interstellar space in August 2012, and the world erupted in celebration, when NASA held press conferences and scientists embraced each other with tears in their eyes, nobody stopped to ask the one thing that should have been obvious. How do we actually know what it measured was real, and not just an anomaly of the specific direction it was traveling? Nobody asked because the achievement was so staggering, so incomprehensible in its scale, that questioning it felt almost ungrateful. Here was a machine built in the 1970s, designed with slide rules and early computers, traveling at 38,000 miles per hour through a void so absolute that the nearest star was still 4 light years away, and it had just become the first human-made object to leave the solar system's protective bubble. The feat felt like the closing chapter of a century-long dream. Scientists declared it done. The textbooks were updated, the world moved on, and 6 years later, a second machine, quieter, less celebrated, launched 16. Days before its famous twin, but arriving at the boundary later due to a completely different trajectory, crossed the same threshold. And what Voyager 2 found when it got there did not confirm what Voyager 1 had seen. It shattered it. Without this new data from Voyager 2, scientists realized they wouldn't know if what they were seeing with Voyager 1 was characteristic of the entire Heliosphere, or specific just to the location and time when it crossed. That single sentence, buried in a NASA press release, is perhaps the most underappreciated statement in modern space science. Because what it really means is this. For 6 years, humanity's entire understanding of the edge of our solar system was built on a sample size of one crossing, one direction, one moment in time. And Voyager 2 just proved that one was not enough. Here is what most people still do not understand about why this matters so deeply. Voyager 2's plasma science experiment can detect the speed, density, temperature, pressure, and flux of the solar wind, and that instrument had stopped working on Voyager 1 in 1980. Read that again, slowly. The instrument that matters most when measuring what lies at the boundary of the solar system. The instrument that directly measures the behavior and temperature of plasma, the electrically charged ocean that fills the space between stars, broke on Voyager 1 nearly 3 decades before it even reached the Heliopause. Voyager 1 crossed the boundary in 2012, carrying the equivalent of a telescope with no lens. It could detect that something had changed. It could register magnetic shifts and particle fluctuations, but it could not directly measure the plasma surrounding it. It was navigating the most scientifically significant crossing in human history with a critical instrument dead and silent. And yet, we built our models on what it told us. We taught it in universities. We published it in journals. We cited it in mission planning documents for future spacecraft. We believed we understood the edge. Then Voyager 2 arrived with the plasma instrument fully functional, crossed into interstellar space on November 5th, 2018, and began transmitting something that stopped scientists in their tracks. Although it took Voyager 1 about 28 days to cross the heliopause after leaving the sun's bubble of influence, it took Voyager 2 less than a day to do so. 28 days versus less than 24 hours. The same boundary. 2 completely different experiences of crossing it. And nobody had predicted that. Nobody had even modeled it as a possibility. Before it crossed the heliopause, Voyager 2 saw the solar wind form an altogether different kind of layer that, oddly, was nearly the same width as the stagnant one seen by Voyager 1. That is very, very weird, one scientist said. It really shows us that we need more data. 2 spacecraft traveling in 2 different directions through the same enormous structure. Finding layers that look strangely similar in size, even though the physics producing those layers seems completely different in each case. The universe is consistent in ways that don't make sense yet. And the moment scientists thought they were beginning to understand the pattern, something else emerged from the data that changed the frame entirely. To understand why Voyager 2's crossing was so different, you need to understand what the heliosphere actually is, because the popular explanation is almost embarrassingly oversimplified. Most people imagine the heliosphere as a neat, spherical bubble surrounding the solar system, a perfect dome of solar influence, uniform in all directions, a clean protective shell that our sun inflates like a balloon against the pressure of interstellar space. That image has appeared in countless documentaries, school textbooks, and museum displays. It is also, according to what Voyager 2 revealed, dangerously incomplete. Voyager 2 took a totally different trajectory, crossing at a different location and revealing that the heliosphere isn't smooth or symmetrical. The structure that surrounds our solar system is irregular. It is asymmetrical. It is, in ways scientists are still struggling to characterize, fundamentally strange. And this is where everything changes, because the implications of an asymmetrical heliosphere ripple outward into questions that touch the deepest foundations of how we understand our own place in the galaxy. Voyager 1 exited close to the very front of the heliosphere, relative to the bubble's movement through space. Voyager 2, on the other hand, is located closer to the flank, and this region appears to be more porous than the region where Voyager 1 is located. Porous. That word is not an accident. Scientists chose it carefully, because what it means is that the boundary separating our solar system from interstellar space is not a wall. It is not even a consistent membrane. In the region where Voyager 2 crossed, particles from inside the heliosphere were leaking through into interstellar space. Solar material, solar energy, the fingerprint of our own star, was slipping through the boundary and bleeding into the galaxy. The heliosphere, the structure that shields every planet in our solar system from the full intensity of galactic cosmic radiation, is not airtight. We only knew that because one probe crossed it in exactly the right direction. Think about what that means for everything downstream. Cosmic ray models, radiation exposure calculations for deep space travel, the baseline assumptions for how much galactic radiation reaches the inner solar system. All of it was built on the assumption that the heliosphere performs a consistent shielding function across its entire surface. Voyager 2's data introduced a variable that nobody had accounted for. Location within the heliosphere determines the quality of the shield. The front might be stronger. The flanks, where Voyager 2 crossed, appear to leak. And the rear, the tail of the heliosphere trailing behind our sun's motion through the galaxy, has never been sampled by any spacecraft at all. We have data from 2 points on an enormous, irregular, asymmetrical, three-dimensional surface. 2 points. And we are using them to model the behavior of the whole. 2 crossings at 2 points on an enormous and lopsided surface are a very small sample from which to judge the shape of the whole heliosphere. It is possible the timing worked out so that the boundary happened to be near the same distance on both occasions, for reasons that have nothing to do with the solar cycle. Scientists will tell you this openly if you press them. The data is extraordinary. The conclusions, however, must remain provisional. Because the universe has repeatedly demonstrated that when you think you have found the pattern, it is waiting to show you that you found one instance of a much larger pattern you haven't discovered yet. And what Voyager 2 found about the plasma itself was perhaps the most significant revelation of all. The Voyager spacecraft have now confirmed that the plasma in local interstellar space is significantly denser than the plasma inside the heliosphere, as scientists expected. Voyager 2 also measured the temperature of the plasma in nearby interstellar space, and confirmed it is colder than the plasma inside the heliosphere, denser and colder. The ocean of charged particles filling the space between stars is thicker and more frigid than the solar environment we live within. That contrast, the warm, thin solar bubble, pressed against the cold, dense interstellar medium, is what creates the heliopause itself. It is a pressure battle played out across billions of miles. And for the first time, because Voyager 2's plasma instrument was working when it crossed, we had direct, in situ measurement of both sides of that battle. Not inference, not modeling. Direct measurement from a probe physically present at the boundary. But there was something even stranger waiting in the magnetic field data. An observation by Voyager 2's magnetic field instrument confirmed a surprising result from Voyager 1. The magnetic field in the region, just beyond the heliopause, is parallel to the magnetic field inside the heliosphere. When Voyager 1 first detected this, scientists weren't sure whether to believe it. A broken plasma instrument, uncertainty about whether the crossing had actually occurred. The magnetic field data was puzzling, but there were too many reasons to question it. Then Voyager 2 crossed, with all instruments functioning, and measured the same alignment. The magnetic field doesn't shift direction at the boundary. It runs parallel across it. And that alignment suggests something profound, that the interstellar medium and our heliosphere are more electromagnetically entangled than we had ever imagined. They are not simply pressing against each other. They are magnetically coupled in ways our theories had not predicted. Research published in early 2024 suggests the heliopause may be shaped differently than once believed. Not a thin boundary line as once thought, but rather a thick boundary layer. This is the updated picture that Voyager 2 helped construct. Not a clean wall between solar and interstellar space, but a thick, complex magnetic transition zone where the two environments bleed into each other, where particles from one side migrate into the other, where the rules of one domain begin dissolving into the rules of the next. The edge of our solar system is not a moment, it is a region. And it is far stranger than anyone thought. Now factor in what Voyager 2 told us about Uranus, and understand that this revelation came not from the 2018 Heliopause crossing, but from data that was collected decades earlier and only fully understood in 2024. In 2024, researchers revisited 38-year-old Voyager 2 data and identified a critical solar wind event that compressed Uranus's magnetosphere just before the flyby, an event occurring only about 4% of the time. Voyager 2 flew past Uranus in 1986 and sent back data that scientists spent decades interpreting. For nearly 40 years, certain peculiarities in Uranus's magnetosphere, its strange tilt, its unusual behavior, were attributed to the planet's fundamental characteristics. Then, someone looked at the archived solar wind data from that flyby and realized that Voyager 2 had arrived at precisely the moment when a rare solar event was compressing Uranus's magnetic field into an anomalous configuration. What we thought was Uranus's normal state was actually a snapshot taken during a 4% event. Everything we built on that flyby data, every model of Uranus's magnetosphere, every planetary science paper, every mission planning document for future Uranus probes, had been built on a misread photograph. This is not chaos. This is the systematic failure of single-point measurements to represent complex, dynamic systems. And it raises the most uncomfortable question in modern planetary science: how many of our other conclusions about the outer solar system are built on similarly narrow snapshots? How many of the facts in our textbooks are actually artifacts of the specific moment a probe happened to fly past, or the specific direction a boundary crossing occurred, or the specific solar cycle phase active when our only measurement was taken? The answer, according to informed sources within the scientific community, is more than anyone is comfortable admitting. Voyager 2 did not simply confirm what Voyager 1 found. It arrived like a second opinion that fundamentally changed the diagnosis. And the scientific community, to its credit, has been honest about the implications, even when those implications are humbling. Before the Voyager probes reached the Heliopause, scientists thought that the solar wind would fade away gradually. But instead, we know that there's more of a distinct boundary, indicated by lower temperature and increased density. The gradual fade was the expected model, a gentle transition from solar dominance to interstellar dominance over millions of miles. What both probes found instead was something far more dramatic: sharp transitions, distinct layers, and a boundary that behaves differently depending on where you cross it and when. But here is where the story shifts from revelation to emergency. Because right now, in the year 2026, Voyager 2 is dying. Not metaphorically, not gradually in some abstract astronomical sense, dying in the most immediate practical engineering crisis sense of the word. Both spacecraft are powered by decaying plutonium and lose about 4 watts of power each year. 4 watts per year. The amount of power it takes to run a single dim nightlight is being lost from each spacecraft annually. After nearly 50 years of operation, those losses have compounded into a crisis. The spacecraft that changed everything we know about the edge of the solar system is running out of the energy needed to tell us anything more. The timeline of what has been lost is stark and irreversible. Since 2024, the dwindling power budget has forced the mission to deactivate 2 science instruments on each spacecraft. Voyager 2's plasma science instrument was switched off in late September 2024, followed by its low-energy charged particle instrument in March 2025. Voyager 1 lost its cosmic ray subsystem in February 2025, and its low-energy charged particles experiment on April 17, 2026. These are not routine shutdowns. Each instrument that goes dark takes with it a window that cannot be reopened. The plasma science instrument on Voyager 2, the very instrument that made its Heliopause crossing so much more valuable than Voyager 1's, has been turned off. The eyes that mattered most are now closed, and the data it was still capable of gathering about the behavior of interstellar plasma as Voyager 2 moves deeper into the space between stars will never be collected. What most people are not seeing is the full weight of that loss. No other human-made spacecraft has operated in interstellar space. The science data collected by the twin Voyager probes is unique. That word unique is doing enormous scientific work in that sentence. There is no backup data set. There is no other probe we can reference. There is no alternative instrument suite, gathering comparable measurements from interstellar space. When a Voyager instrument shuts down, the data it would have collected simply ceases to exist. The gap opens in humanity's knowledge of the universe that will remain open for decades, possibly forever, because no funded, approved mission to interstellar space is currently on any agency's active schedule. But then, just 2 days ago, on August 4th, 2026, something happened that almost no major news outlet covered adequately. Engineers at NASA's Jet Propulsion Laboratory completed a high-stakes power swap on August 4th, 2026, a simultaneous procedure nicknamed the Big Bang that preserved the spacecraft's 3 remaining science instruments in deep space for at least 1 more year. The Big Bang. That is what NASA's own engineers called it internally, a procedure so risky, so delicate, and so consequential that its failure would have ended Voyager 2's science mission years ahead of schedule, and its success, which they achieved, bought humanity 1 more year of data from the only probe operating in interstellar space. The 3 instruments the Big Bang preserved function as a continuous weather station at the outermost edge of the sun's influence, providing data that helps scientists understand how the Heliosphere shields the solar system. 3 instruments: a magnetometer measuring the interstellar magnetic field directly, a plasma wave subsystem detecting electromagnetic waves that reveal the density and behavior of the ionized gas between stars, and a cosmic ray detector mapping the radiation environment that Voyager 2 moves through as it pushes deeper into the galaxy. 3 instruments, 12.8 billion miles from Earth, kept alive by an engineering maneuver that had to be executed perfectly on the first attempt. The thermal constraint is precisely why the Big Bang procedure required switching multiple devices simultaneously rather than sequentially. Some devices must stay warm during the transition, and the entire load calculation must work out from the first moment the swap occurs. In interstellar space, there is no warmth. There is no ambient temperature that keeps electronics functional. The probe's own power systems generate the heat that prevents its instruments from freezing into permanent silence. Turn the wrong thing off in the wrong order, and a component drops below its minimum operating temperature and fails permanently, with no possibility of repair, no possibility of a service mission, no possibility of a second chance. The engineers at JPL executed the procedure knowing that any mistake would be final. Without the Big Bang activity, the mission would have had to turn off another instrument on Voyager 2 before the end of 2026. The savings should provide power to keep its 3 instruments operating for at least an extra year. 1 year. That is what a flawless execution of one of the most technically demanding remote engineering operations in history purchased. 1 year of data. 1 year of transmissions traveling at the speed of light for 16 hours and 58 minutes before reaching a receiving dish in Canberra, Australia. 1 year of readings from a place no other human instrument has ever been or is likely to reach again in any of our lifetimes. The real story is not that Voyager 2 is dying. The real story is what it still has to say before it goes silent, and whether we are listening carefully enough to hear it. Because what Voyager 2 is traversing right now is not empty space. The region it is currently moving through, the local interstellar medium, is itself a dynamic, structured environment. Interstellar space is dominated by the plasma, or ionized gas, that was ejected by the death of nearby giant stars millions of years ago. The material Voyager 2 is measuring as it moves through interstellar space is the ancient debris of stellar explosions. The plasma surrounding it was blown outward by supernovae that occurred before the Earth even formed. Every reading Voyager 2 sends back is, in a very real sense, an archaeological survey of ancient cosmic violence. And the probe is moving through this material at 34,000 miles per hour, slowly mapping a tiny corridor through a region that spans light years in every direction. What the data suggests about this region is unsettling in its complexity. The interstellar medium is not uniform. It has structure. It has variation in density and temperature and magnetic field orientation. And as Voyager 2 moves through it, the readings change in ways that tell scientists something is happening out there that their models are only beginning to capture. Something else, perhaps the pressure of the interstellar medium the sun is currently moving through, or the way changes in the solar wind take time to travel out to the edge, may matter as much as the sun's immediate mood. That is a genuine open question, not a solved one. The position and behavior of the Heliopause, the shield wall between our solar system and interstellar space, may be influenced not primarily by what our sun is doing, but by what the interstellar medium surrounding us is doing. External pressure from the galaxy itself may be shaping the boundary that protects every living thing on this planet from the full intensity of galactic cosmic radiation. We are, in other words, not simply broadcasting our existence into a passive void. We are moving through a structured galactic environment that is actively interacting with our solar system in ways we are only just beginning to measure. And our only sensor in that environment is a 49-year-old spacecraft running on steadily depleting plutonium, operating on the engineering ingenuity of a team at JPL that keeps finding new ways to squeeze 1 more year of science from a machine that was designed to last 5. The broader implications for future space exploration are staggering and, frankly, somewhat alarming. The probe has enough power to continue exploring this region with at least 1 operational science instrument into the 2030s. Into the 2030s, meaning within a decade, probably. The last instrument on Voyager 2 will fall silent. The last data packet will travel 16 hours through the void to reach Earth. The last new measurement from interstellar space will be recorded, and then there will be nothing. Two silent hulks of 1970s engineering, still moving, still traveling deeper into the galaxy at tens of thousands of miles per hour, but no longer listening, no longer speaking, no longer reporting what they find. And there is currently no approved mission to replace them, no probe with an approved budget, a confirmed launch date, and instruments capable of operating in interstellar space is in active development at any space agency on Earth. The interstellar probe concept has been studied, papers have been written, scientists have made the case for it with increasing urgency. But the gap between scientific urgency and political will to fund deep space exploration has rarely been wider. According to informed sources within the planetary science community, the loss of the Voyager probes will create a decades-long blind spot in humanity's knowledge of the heliosphere and the interstellar medium, a void in our data that will fundamentally limit our ability to plan crewed missions beyond the solar system, model radiation environments for deep space travel, and understand the full scope of the cosmic environment in which our civilization exists. Think about what that means for the long-term ambition of becoming a spacefaring species. Every serious discussion of crewed missions to Mars, to the outer planets, or eventually to other stars, requires an accurate model of the radiation environment those missions will traverse. The heliosphere is the shield, understanding its shape, its consistency, its porosity, its behavior across the solar cycle. All of that matters directly to the survival calculations for human crews beyond Earth's magnetosphere. And the only probes we have ever sent far enough to measure the shield from the outside are Voyager 1 and Voyager 2. When they go quiet, we lose the only direct measurements we have of what that shield actually looks like from the galaxy's perspective. What Voyager 2 accomplished that its twin could never fully achieve was this. It gave humanity a second perspective, not just a second data point, but a second angle of view on a structure so vast and complex that no single angle of view could ever be sufficient. It proved that our first understanding was incomplete. It proved that the heliosphere is asymmetrical, porous at the flanks, magnetically entangled with the interstellar medium in ways that defy simple models. It proved that the solar wind doesn't fade. It ends, suddenly and sharply. It proved that the plasma beyond the boundary is denser and colder than our models suggested. And it proved that the single most valuable instrument for measuring the boundary of our solar system, the plasma science experiment, was broken on the only other probe we had. Voyager 2 didn't just do something Voyager 1 never could. It corrected something Voyager 1 never knew it had gotten wrong. And in doing so, it did something far more important than confirming our expectations. It revealed how large the territory of our ignorance still is. Right now, as you read this, the Big Bang procedure has just been executed. 3 instruments are alive in interstellar space when they should not be, kept functioning by the ingenuity of a team of engineers working to preserve something irreplaceable. The data is still coming in. The magnetometer is still measuring fields that have never been measured before. The plasma wave subsystem is still detecting electromagnetic whispers in the space between stars. The cosmic ray detector is still counting particles ejected by supernovae before our sun was born. But the clock is running. 4 watts per year, bleeding away. Plutonium slowly decaying into silence. And the question that nobody is adequately answering, not in the press releases, not in the congressional budget hearings, not in the public conversation about space exploration, is what happens to humanity's understanding of its own cosmic environment when the last Voyager instrument finally goes dark. What do we do with a gap in our knowledge that spans the distance between our solar system and the rest of the galaxy, filled only by 2 probes that were designed to survive 5 years and managed nearly 50? The universe is not waiting for us to be ready. It is out there, complex and asymmetrical and magnetically strange, doing things our models haven't predicted, and our instruments are too few and too old to fully capture. Voyager 2 crossed a boundary that Voyager 1 crossed first, but it crossed it differently, saw it differently, and reported back something that changed everything we thought we knew. And the most urgent question is not what Voyager 2 found. It is what we are going to do about what we don't yet know, because something larger is coming, either a new understanding of the space surrounding our solar system, or a long and expensive silence while we wait for the courage and the funding to send something new into the dark. The edge is out there, the data is still arriving, the clock is ticking. And the next page of this story has not been written yet.